Hi everyone. We are happy to present Query2Uncertainty, our CVPR2026 paper on robust uncertainty quantification and calibration for 3D object detection under distribution shift. This is joint work from the Institute for Automotive Engineering and the Computer Vision Institute at RWTH Aachen University. What you're looking at is a 3D object detector running on 6 multi-view cameras. Each detected bounding box comes with an uncertainty ellipse and a score bar, an estimate of how confident the model is about where exactly this object is in 3D space and how certain it is about the object's class. But here's the problem. Are those uncertainty estimates actually trustworthy? What happens when the sensor data gets noisy, or the scene looks nothing like what the model was trained on? In our work, Query2Uncertainty, we answer this question, and we propose a method that produces reliable regression and classification uncertainties even when the input distribution shifts away from training data. The standard fix for uncalibrated detectors is post-hoc calibration. After training, you fit a lightweight function, like temperature scaling, that maps raw model outputs to better calibrated probabilities. It works well on in-distribution data, but it has a fundamental flaw. The calibrator is fitted once on the clean calibration data and then blindly applied to every test input, regardless of how different that input looks from training. When sensor data is affected by adverse weather, unseen objects, or geographic shifts, the calibrator performance decreases, giving you wrong uncertainty estimates like an uncalibrated model. Our key question: can the detector itself tell us how familiar a detection is? If we can measure how in distribution a query is, we can make calibration adaptive, pushing uncertainty up when the model is on unfamiliar ground and keeping it tight when it's confident. Our method builds on DETR-style 3D object detectors. These models maintain a set of learnable object queries inside a transformer decoder. Each query attends to sensor features and, after several decoder layers, produces one detection: a class score, a 3D box, and associated uncertainty estimates. Here's the key observation: that final query vector is a rich, compact representation of the hypothesized object. It encodes class, location, and detection confidence. It's the ideal signal for density estimation. After training the detector, we run a forward pass on the training set and collect all query vectors corresponding to true positive detections. Per object class, we fit a normalizing flow, a real NVP, to model the distribution of these 256-dimensional feature vectors. At test time, each query gets a scalar density score. How likely is this query under the training distribution? A well-seen car in clean conditions corresponds to high density. A blurry shape under sensor noise corresponds to low density, far from the training manifold. We inject this density signal into classic post-hoc calibrators. For classification, we replace standard post-hoc calibrators with a per-detection uncertainty signal that increases as the density drops. The less familiar the query, the more we inflate the uncertainty. For regression, we apply the same density-aware scaling to each predicted variance: box position, size, and yaw. No retraining of the detector is needed. This is a lightweight, drop-in, density-aware post-hoc module. Our second contribution is a unified uncertainty evaluation framework for 3D object detection built on top of new scenes. It's an easy-to-use framework for uncertainty calibration and evaluation. We adapt DECE, the detection expected calibration error, and LAECE, localization aware expected calibration error, for classification calibration. For regression, we use the MCA. Miscalibration area for box centroid, box dimension, and orientation. All metrics are averaged class-wise across all 10 new scenes categories to prevent the frequent classes from dominating. On in-distribution data, our density-aware calibrators consistently outperform deep ensembles, Monte Carlo dropout, train time calibration methods, and standard post-hoc methods for classification and regression. To test calibration performance under distribution shift, we use multi-corrupt, which consists of 10 camera and LiDAR corruptions at 3 severity levels. Additionally, we perform a geographic distribution shift experiment using samples from Boston for training and calibration, while evaluating calibration quality on samples captured in Singapore. In both distribution shift settings, the standard post-hoc calibrators fall back in their calibration performance. Our density-aware variants consistently outperform their counterparts, tested on both a multi-view camera and a LiDAR-based detection model. The density signal effectively identifies that something has changed in the input and adjusts confidences accordingly. To summarize, Query2Uncertainty is a lightweight add-on for any DETR-style 3D object detector. By fitting a normalizing flow on the latent object queries, we obtain a density signal that makes post-hoc calibration robust to distribution shift for both classification confidence and bounding box regression uncertainty simultaneously. The code and our new uncertainty benchmark are open source. Link in the description. Thanks for watching.